First of all, good afternoon, and thank you for having me here at AGI. It's my pleasure to present two different papers that share something in common, and what they share in common is the role that geography plays in regional economics and in specific regional economic growth. So I've been mostly interested in regional economics, spatial econometrics, and economic geography, and I'm writing two papers with two different teams, and I would like to present both of them briefly. That means that I'm planning to have around 20 minutes per paper, so I would like to set first a timer here so that I don't talk for too much. There you go. So as Alvaro said, my name is Felipe, and I am a PhD candidate at TU Dresden in Germany. And I would like to first talk about one paper here. And this paper is named Three Border Areas and the Location of Economic Activity in Open Economies. And it's written with my boss in Germany, who is Christian Lessmann. We both work at the Chair of International Economics in TU Dresden. And what's the motivation of this paper? The motivation, I would say, can be summarized by this simple figure, this bar plot. And this bar plot actually answers the following question: is, on average, do border and non-border regions have the same level of economic activity? Here we're talking about subnational regions. So think about a region in the center of Brazil, and think about a region in the border next to Argentina or Colombia. Would those regions on average have the same income level? Now, if we have a worldwide sample, we find that actually inland regions are richer than border regions. And that makes sense because border regions have been cut from the market of the other country. So they have a border that separates them from a market, if you want to put it in simple terms. And this figure here shows that, however, if there is a regional trade agreement between those two neighboring countries, then the inland regions, or let's say the non-border region and the border region, have the same level of economic activity. But in darker gray, you can see that a border region without a trade agreement with that neighboring country is on average much poorer. Now, this is the motivation of the paper. Now, what is the research question? The research question is, what is the causal effect of regional trade agreements among neighboring countries on the economic activity of areas near the international border? Because we're talking about inland or land international borders as well. We are not going to consider island countries such as Australia or New Zealand or Japan or the Philippines. We're just considering inland borders. Now, there is a large body of literature that tries to relate trade and the location of economic activity. And if you think of, for example, economic geography and the seminal papers of Krugman, that was the main idea behind. How does economic activity locate itself within a region, within a country, and how are these agglomeration forces, or how do they shape the location of economic activity? Why some regions specialize in certain products, and how industries agglomerate there, and how other regions do not agglomerate, or do not agglomerate industries and do not have factories, etc., etc. So we have this inequality between regions, and all that literature that talks about that. Moreover, thank you. Moreover, we have other papers that are more empirical, such as the paper by Mr. Lessmann, my boss, or some reports by the World Bank, for example, about the importance of economic geography in today's world and development. And there is a very nice paper, this one by Brulhart, that summarizes somehow what we know so far about economic liberalization and economic activity, which is, and I read here the quote: the tendency for trade liberalization to favor relocation toward border regions emerges as an almost ubiquitous result. Meaning that when there is trade liberalization, factories, for example, would go to the border because there is a new market that has been opened beyond that land border, for example. So we have also some other literature that is related to trade openness and international borders. And here we have some papers, for example, that try to measure the impact of trade agreements and trade on the economic activity of border regions. For example, some of them use the light emissions, nighttime light emissions, or near international roads. So roads that go from one country to the other, and then if there is trade openness, those roads are usually brighter at night because there is larger trade, for example. So there is this kind of literature that tries to emphasize the importance of trade openness and the location of industries, the location of factories, the location of cities themselves near those borders. And moreover, because I'm going to talk about night lights as a proxy for economic activity, I will talk a bit about some of these papers that you see here in the bottom of the slide. So we have the seminal paper by Chen Nordhaus, which, if I'm not wrong, was published in the American Economic Review. And in this paper, they show that actually, whenever we don't have GDP data, we can use night times as a proxy. And they show that if we compare data for GDP and data for night lights, these two are actually highly correlated. So whenever we do not trust the statistics or we do not have them, then nighttime lights are probably one of the best proxies for regional or national economic activity. As a summary, as a proxy, it's not perfect, but it's one informative source. And of course, my supervisor, my boss, also works a lot with it. So he has also a very interesting paper about that. But this is just like I'm just summarizing a quite large body of literature that uses night times as a proxy for economic activity. Now, let me go beyond the literature and start talking about my paper or our paper. So here, we're going to focus on 3 points. Now, what are 3 points? 3 points are the points where the borders of 3 countries meet. So, for example, sorry, can anybody please confirm if you can see my pointer on the screen? Yes? Great, thank you. So, for example, the pointer, I have it here in South America. So we have the 3 border between Uruguay, Argentina, and Brazil, if I'm correct here. So that would be one of those 3 points. We have 3 countries, 3 land borders that meet. Overall, there are about 150 of these 3 borders, 3 border points throughout the Earth. You can see, for example, that obviously, as I said before, we do not consider islands. So Japan is not considered in this data set. Australia will not be considered. Some countries in Central America as well. Now, what is the identification strategy? So remember, we want to study the impact of free trade agreements on economic activity. So we're going to use a quasi-random treatment or experiment, which is the beginning of a regional trade agreement in that triplet. So for example, I have 3 countries here. We have Serbia, we have North Macedonia, and Bulgaria. Now, those 3 countries did not have a regional trade agreement by 1992, and it remained like that until 1999. In the year 2000, there was a regional trade agreement between North Macedonia and Bulgaria. That would be the treatment. However, as it's a common place throughout the world, regional trade agreements are expanding and expanding. So by the year 2004, there was 1 more trade agreement in that triplet. And by the year 2010, there were 3 trade agreements in that triplet, meaning they were all fully connected in terms of trade agreements. Now, we're going to consider as the pre-treatment, the period where there were no trade agreements, and as treatment, the period in which there was only 1 trade agreement, meaning that pre-treatment, in this case, would be from 1992 to the year 1999, and treatment from the year 2000 to the year 2003. Now we're going to use a very nice data set by Mario Lasch, who is a professor in Germany, and he has this huge database where you can find all the trade agreements throughout the last 30 years, if that is correct, about 1990. And we have information on more details of the trade agreements, but for now, the project is just considering if there is 1 trade agreement. They come, as you may know, in different flavors. Regional trade agreements just for services, or just for goods, or trades, or services and goods, etc., etc. But we're just considering the existence of a regional trade agreement. Now, how is economic activity measured? Well, we have the triplet of countries. We have the 3 point, that dot on Earth, and we are going to create some buffers. Some buffers meaning some circles around that point. Circles with different radii, for example, from 25 to over 120, something here, something like that. You can see here on in the image in the left. If you go to the right, then it's a closer view of that buffer with a radius of 75 kilometers. Now, how is economic activity measured? As I told you before, we're going to use nighttime lights. Now, you may ask, well, why don't you use GDP data? Well, basically because there is no GDP data published for this kind of radii or for this kind of buffer areas. So because we use as a robustness check the variation of the radii, yes, of the radius of that buffer, then we are going to consider nighttime lights as the proxy. Luckily, we can get nighttime lights from 1990 until 2022. And actually, in the year 2020, a team of researchers here from Asia harmonized the data from different satellites that we have. So we have some satellites working in the 90s, measuring nighttime lights, and some different satellites in the late 2010s, and they harmonize all this data so that we can study the variation over time. So here we have yearly averages of 1 year and the other, all the way from 1992, in this case of this paper, we're going to use it from 1992 to 2020. And in case you're not familiar with this type of data, it's a raster, meaning that we have pixels, and each pixel is assigned a number from 0 to 63, being 63 the brightest indicator of lights, and 0 no lights as an average over time. Sorry, as an average over time, I mean as an average for 1 year, because we have daily data for these rasters. Now, what is the final data set of 3 points and regional trade agreements? Is the following. Now we have, as you can see, many 3 points in East Europe, some of them in Africa, some of them in Asia, but only 2 in the Americas. With a more restricted data set with about 40 3 points. You can see the details in the working paper. And remember, we have to have this variation. No regional trade agreements, and then at least 1 year in which we have only 1 regional trade agreement. And that's why, for example, we have very few points in the Americas, because that area integrated in the 90s, early 90s, and in most cases as well, the 3 countries integrated at the same time, meaning that we don't have that treatment of only 1 pair in that triplet. Now we're going to use 2 different empirical strategies. First, difference in differences, and we're going to use the simplest model for difference in differences, which is basically a regression of the lights that are recorded for that area within that country, within that buffer. And we are going to use this RTA indicator as a dummy variable. If there is a regional trade agreement or not with your neighbor, in what year, here, indicated by the T index, we're going to use triplet and country fixed effects, and we have an error term. If you have any questions about the empirical strategy, we can go further into the details. As is common in the diff in diff literature, we're going to use the event study design to show that there are parallel trends. As you may know, when you use diff in diff, you need to convince your audience, and you need to show that treatment and control groups follow the similar or a parallel trend in this case, in terms of lights. Meaning that there was not a break or a structural break in the treatment group or the control group before treatment. And that will be shown in this plot by having the coefficients of this regression as 0, as not statistically different from 0 before treatment, and then statistically different from 0 after treatment. Great. So what are the results? I have many columns, as you can see here, because I have different samples and I use different standard errors or cluster errors. Different samples, excuse me. Different samples meaning that in for example, column 1 and 2 have the same sample, but different standard errors, but 3 and 4 is going to be a reduced sample in which I remove observations for which I do not record any light. So there are some really dark areas, for example, in certain countries in Africa, near the international border. I'm going to remove them if I do not record any light on any given year. I remove that observation. Now, 5 and 6 is a bit more strict, and I'm going to remove the entire country if there was a year in which we don't have any lights, okay? And here you can see that when I have a radius of 50 kilometers, you start to find the significance in that coefficient. And here we have the number of triplets as 27 and 36 countries. However, if you change that radius, it's going to slightly change, and that makes sense because then we will have to control for other variables. Just because when you make the radius so large, you may even cover an entire country or different subnational regions of a country, and then you will have to control for different variables that affect the growth of those regions. Think of population, for example, the structure of the economy, even the temperature, altitude, so many other factors. So by having that small radius, we somehow make sure to a certain extent that those regions have similar growth fundamentals. We can discuss more details regarding this in the next few minutes. But whenever I show those regression estimates, you may think, okay, well, that's the effect that I want to convince you, right? That this treatment, regional trade agreements, impact the economic growth of those regions as proxied by lights. However, when I have the event study plot here, you see that the coefficients are somehow relatively similar to 0, meaning parallel trends, yes, to a certain extent, but after treatment, they are also not statistically different from 0, meaning there is no effect when we take a look at this event study plot. What we want is the coefficients after treatment to be different from 0. So what we did was, okay, we were working with regions. Maybe regions are not the best units for measuring the changes that free trade agreements will trigger. We would like to focus in cities. And we have a large data set of cities for the entire world. And that data set has been recently used by Bloom and his co-authors in a 2021 paper. And it has data for 1990 cities and for 2015 cities, over 20,000 cities. And they define a city as a cluster of over 40,000 inhabitants and some other characteristics. And they define those clusters as cities. We're going to work with those cities. Now, what does that mean in our project? Take a look at the city polygons in 1990, the figure in the left. The cities will be these gray small clusters. Those are cities detected with their algorithm. So we're going to measure the light within those small clusters, here by delimited by this gray line. And then when we measure, or when we find cities in 2015, we were going to find more cities, as you can see, more of these gray pockets. And then we're going to measure lights within those clusters of pixels. Here I'm showing, for example, Israel, Syria, and Lebanon. And you can see that there are many more cities in the year 2015. And we can run the same regressions. Now let's take a look at this regression for the year 1990, cities in 1990, with a radius of 50 kilometers. We do not find any significance. However, when we work with data for 2015, we start to see what we were expecting. Coefficients that are not statistically different from 0 before treatment, meaning parallel trends, and statistically different from 0 a few years after treatment, so a few years after the regional trade agreement. That's for the year 2015, and a radius of 50 kilometers. If we go beyond to 55 kilometers, we even find more significant coefficients. However, we have to relax a bit the parallel trends assumption, because for at least 2 years, they're statistically lower than 0. We want it to be statistically not different from 0. And the same happens for 60 kilometers. That's, let's say, a small issue whenever we include the radius of that buffer. And here you can see the different samples, because as I told you before, different columns mean different restricted samples. For example, the regional sample in this case, had many countries and triplets in East Europe, some in the Middle East, and some in Africa. But when we have the restricted sample, we're only considering some triplets in the Middle East, East Europe, and only 2 in Africa. So far, this is the first paper, and I can summarize it with these 4 sentences, that we don't find the significant effect of RTAs on economic activity for buffer areas in general. Also, we do not find that effect when we focus on the 1990 cities. However, when we focus on the cities that were detected in 2015, we find, to a certain extent, a significant effect of RTAs on economic activity as proxied by nighttime lights. And that means that RTA appear to be driving the agglomeration of output in cities or population growth. Here, we'll have to give a more detailed interpretation of nighttime lights because we do not measure population for those cities. What is something that we would like to do next? We would like to study the heterogeneous effects of RTAs. That's what I'm working right now. So I would like to see if in Africa, the effect is different if we compare just to Asia, if we restrict the samples to those geographical regions. And also we could think of the heterogeneous effect of different types of regional trade agreements, as I said before, only goods and services, etc., etc. And moreover, if you are familiar with the different estimators, you could notice that in my plot, I already used one more estimator, the traditional two-way fixed effect estimator, but also the San and Abraham estimator, but there are also other estimators like the Goodman and Bacon, Calway, Santana, and more coming. So this literature is evolving quite rapidly. That's all for the first paper. It took about, 20 minutes. Now let's talk about the second paper, which is, if you want, more related to the work of this institute, because we're going to focus on only provinces, still regional economics, but provinces of China. And here I'm working with a different team. I'm working with Professor Carlos Mendez from Nagoya University here in Japan, and with Linda, who works at the University of Hagen in Germany. And we are going to focus on spatial filter. So what would be a region without neighbors? And that's why the title of the paper is When Regions Grow Solo, Neoclassical Convergence, Spatial Filtering Across Chinese Provinces. Now, what is the motivation? Well, first of all, the estimates from the augmented solo growth model are biased, and they are biased by definition because they do not consider the effects of neighbors. So when you see these models, they consider that a region grows by itself. It depends on the determinants of growth of that region, but not on what is happening around that region. And we can see that that's biased. We can discuss also about it in detail if you're interested. And because this opens a new field, which is spatial causal inference, which is just a field that is slowly evolving, right? Because we need to talk about the effects of one region on a neighbor region, but then we are also here thinking about the links in terms of causality. This is something we can talk later. Now, what is one more motivation? Well, there is limited research on the effect of geographical links and convergence accounting across Chinese provinces. There are some studies that talk about other subnational regions of other countries. That's why we like to focus on China. Also, I would like to say that we found a really nice data set for China. And moreover, we're in contact with the person who created that data set. So we're really happy about the data set we're going to use. And I'll explain later on what that data set is. What would be our two research questions? Well, first of all, to what extent the role of space effects, neighbor effects, is affecting the convergence of Chinese provinces, Chinese regions? And what are the contributions of capital inputs and productivity on the convergence of provincial income per capita? We're going to use different methods, and I'll try to summarize them so that at least you get a high-level intuition of what they mean. I'm going to use 4 of them. We're using 4 of them. The classical convergence framework, which I think most of you know. And there are many papers, but there is a seminal paper if you want to point at one, which is Barrow and Sally Martin in 1992. Then we have convergence growth accounting, which is a more recent framework by Wong and Farah in 2007. And we have a statistic that measures the agglomeration, or let's say autocorrelation of data, which is the more ANSI, which was developed many years ago. And we're going to use the Getis filter, which was created in 1995, but somehow is still used. And actually, this is being somehow compared to other spatial filters. And that's why I also mentioned a 2010 paper. The outline of this presentation will be the following. I will talk about the data and how we constructed the data set. I'll talk a bit about the methods, the four methods or the three methods related. If I talk about convergence accounting and convergence regression as one, and then I'll talk about related literature, some results, and concluding remarks. There is a lot that still needs to be done regarding this project. So if you have, in general, if you have any comments or questions, please feel free to ask them later during the Q&A period. Now, what is the data set? Well, this data set is a data set for 31 provinces over the 1990-2017 period. And we have data for GDP per capita, real GDP in constant 2010 prices. And this data come from the National Bureau of Statistics in China. Then we have this human capital data, which is human capital index. Yes. So if somehow we think of human capital in this data set as a GDP per capita measure in terms of a monetarization of human capital. So how much value does the human capital on average have in this region or in these provinces? And this index was created by Barbara Fraumeni, who is the person who's already read this manuscript and is giving us some input also to improve the quality of the paper. Then we also have the capital output ratio, which is the current provincial physical capital divided by the current provincial GDP. And now let's talk about a spatial autocorrelation. Now, what is a spatial autocorrelation? When you see these images, you can think of spatial correlation as measuring patterns. So for example, positive spatial autocorrelation meaning that if blue, for example, think of blue representing high GDP and white representing very low GDP, meaning that blue in the positive spatial autocorrelation is or regions that are rich are clustered. So regions in blue that are very rich are surrounded by regions in blue, which are very rich. And regions that are representing white, poor regions, are surrounded by poor regions. That means positive spatial autocorrelation. Regions are surrounded by similar regions in terms of this variable, for example, income per capita. No spatial autocorrelation is basically randomness. And negative spatial autocorrelation, which is very unusual in the real world, meaning that a rich region is surrounded by a poor region, which is surrounded by a rich region. You may think of high inequality cities in Latin America, for example, where you have some slums, and then next to it a very rich neighborhood, and then a slum and a rich neighborhood. That's something you could see in a city. But for countries and provinces, you rarely see negative spatial autocorrelation. Now, what is the Getis filter? The Getis filter wants to exploit the spatial autocorrelation of the data in order to remove it. How do you do that? You use this filter, meaning that a filter, in this case, a spatial filter, removes that spatial component, that neighbor component, meaning that it would turn regions that have neighbors into isolated regions. So what would be this region without its neighbors? And this spatial filtering of the data can help us to avoid misguided interpretation. Why? Because sometimes when you run regressions, the traditional OLS regressions, you find that the error component of your regressions is autocorrelated, is not random. And that's one of the assumptions of OLS. We can avoid such type of misguided interpretation by using spatial filters. And so perhaps here talk a bit about spatial econometrics in case you are not very familiar with the terms. In spatial econometrics, you often model space. So you want to run your regressions and you add some terms to your regressions that model the interaction of these regions or units. For example, by adding spatial lights, but if you don't know about it, don't worry about it. That is this WI, but it's not important for now. That's one way in spatial econometrics. You model space. One more way would be to filter. So try to remove the effect of space and then you run your regressions. That's the approach we take in this paper. And if you want, that's the novelty of this paper. We integrate convergence, a convergence framework, a convergence accounting framework, and a spatial filtering framework. Something that, as far as we know, is not being used before. And in case you don't know about beta convergence, well, it's basically the inverse relationship between the initial level of any variable and its subsequent growth rate. If we focus on income or income per capita, it's quite intuitive, meaning that, for example, rich countries here, initial level of Y, think of Japan, for example, in the year 2010, a relatively rich country, has grown quite little. When you compare that to a country like, let's say, Peru in South America, which was much poorer in the year 2000 or 2010, it was growing faster. Yeah, so we see growth rates in terms of Japan, for example, of below 2%. That's kind of the standard in Japan in the last few years. And when you compare that to a country like Peru, that can be growing at 4, or a country like China that could be growing about 7. So that's the poorer countries growing faster, the rich countries are growing, but to a much slower rate, to a much smaller rate. And that inverse relationship can be shown in this equation, and we're going to use that equation, which is basically derived from a solo model, and we're going to decompose, first of all, this growth account, or we're going to show this growth account in decomposition, which is based on the solo model. So as you may know, the solo model just have capital, we have income, we have A, which is the productivity, H, that is human capital, and L, that is labor, in our case, population, because we don't have data for labor at the provincial level for such a long span of time. And that, if we take logs, can be turned into the second equation. Now, if you have that second equation, then you can also take derivatives and show that the growth rates have to follow the same, a similar relationship. And then this equation can be written as the last decomposition, meaning that the growth of income per capita is basically the sum of the growth of the other inputs in the growth equation. Now, we want to go beyond growth, and then we're going to talk about convergence. And that's where convergence accounting comes. So basically, we have our standard Barrow regression, and then we're going to decompose this beta coefficient into the 3 coefficients related to each of the inputs. So basically, you will have a beta for capital, a beta for human capital, and a beta for productivity. So that's the standard in the literature, let's say, of the convergence accounting. Now we want to go beyond. So we are going to talk about spatial convergence accounting. What does that mean? That we can have the same production function and show that the growth of the human, the level of of income per capita is going to be equal to this sum of variables that are spatially filtered and then a net spatial residual. Meaning that, again, we can have this equivalence of growth rates, and we're going to show that the growth rate of income per capita is going to be equal to the growth rate of capital plus the growth rate of human capital plus the growth rate of technology. All of them filter plus the growth rate of this net spatial residual. And again, we're going to have these beta coefficients associated to each of those growth rates. And that's basically the model. Now, literature. In terms of convergence of Chinese provinces, there are many, many papers, as is the case for any other country, but many of them do not show the effect of neighbors or the role that, in this case, spatial econometrics can have in explaining convergence patterns. So overall, I'm just mentioning here 3 papers, but there are many more. Now, in terms of convergence and spatial filtering, then we have other examples, such as the paper by Fisher and Stampner, in which they used regions in Europe, and then they filter income per capita, and then they study convergence. We also have some studies for Brazil, one study for Indonesia that I wrote with a colleague from the Department of Planning of Indonesia, and with Carlos Mendes from Nagoya University. We have some studies for Spain, and we also have a study for China. However, in this study of China, the 2 authors from Spain, if I'm not wrong, Villaverde and Massa, they use a different convergence framework. So they are not using this convergence accounting framework, but they use a much simpler distributional convergence framework. I'm not going to go into the details, but again, if you have any questions, just please ask me, because I also worked before with this type of convergence framework. And what are basically the results? Now, first of all, we want to filter data that is spatially autocorrelated, meaning we want to filter data that shows spatial patterns. In this case, you can see in this table that we have some variables. For example, the trend because we use the Hodrick-Prescott filter because we want to avoid the business cycle effects. And we have that for the year 1998 and 2010, spatial autocorrelation, which are the numbers shown here in the table, are statistically significant. And here the columns are going to be different neighbor structures, spatial weight matrices, meaning that, for example, k equal 4 means that only you consider the 4 closest regions as your neighbors, or the 5 closest regions as your neighbors, and 6 as your 6 closest regions as your neighbors. Here, this distance band, in the case of China, is the minimum distance for which all regions have at least one neighbor, which is about 1,000 kilometers. You can then see that we have all the variables of our growth equation, but also some that I call tilde. Here are the ones that are already spatially filtered. And as you can see, once you filter the data, it doesn't show any pattern of spatial autocorrelation. That's why the statistic is not significant. So there are no stars, if you want to see it that way, for the spatially filtered data. You can see as well that we're using 2 years. So in this case, it's a cross-sectional study. Maybe a further way to improve this paper is to work with panel data. We need to discuss this in the future. But as you can see, we have only 1998 and 2010. And you wonder, well, why those 2 years? And we're choosing those years because those are the years for which systematically, from beginning to end, data is spatially autocorrelated, meaning spatial effects are quite strong, if you want to describe them like that, between 1998 and 2010 for all those variables. Once we filter them, there is no spatial autocorrelation. If you are a bit lost, I'll just go back to the figure. That means that we end up with this figure, like it's in the middle, spatial randomness in terms of all the variables of our growth equation. Now, what do we do next? Then we're going to first show you how does GDP per capita change once we filter the data. So you can see here in 1998, in the top left of the slide, we have the log of GDP per capita. And then B, the bottom part, would be the log of the filtered GDP per capita. So you can see, for example, that regions that were somehow poorer in the western part of China, once you filter them, will become rich. Meaning that if those regions somehow did not have their neighbors, they would be slightly richer. In contrast, regions in the east here were on average richer in 1998, but when you filter the data, they become slightly poorer, meaning that regions that are surrounded by rich regions have somehow a higher level of income per capita. Yes, in the sense that once we filter, when we use this spatial filter, they will be on average poorer. The same for the case of 2010. So regions in the, for example, regions in the west, a little bit poorer, surrounded by poorer regions, they become slightly richer.
If you have 10 more minutes, okay?
Thank you. If we filter the role of space, let's say if we use the spatial filter. Now, this again, it's common in the literature of Chinese provinces and convergence, because we see that there is this divide, no? The coastal areas of China being much richer, with access to foreign markets, with manufacturing as one of the base of their economies, exporting towards, let's say, out of China, and east, we have western inland regions that are much less connected and are much poorer. That's an east-west divide that you can see in these figures. Now, what are the results of absolute convergence? Well, the original data and the filtered data both show patterns of convergence. You can see here these two figures where we have on the x-axis the initial level of GDP per capita, and on the y-axis the overall growth rate from 1998 to 2010. Now, the main result of this paper can be summarized with this table. Now, what does this table show? it shows the contribution of each of the inputs in your our growth equation and their contribution to the overall convergence. So model 1 is a traditional model without the role of space. Here we have that aggregate efficiency, which is sometimes called technology or total factor productivity, explains about 70% of the convergence of Chinese provinces over this period. Capital inputs explain about 30%, with physical capital explaining about 13% and human capital 16%. Now, this is the traditional standard model in the literature. In this new interpretation that we give to the augmented solo model, then we have the role of space, and we can study the contribution of space. And what's the contribution of space? Well, aggregate efficiency, or the contribution of aggregate efficiency, does not change much. It's about 70%, but the capital inputs have a much lower contribution. Physical capital, although it increases, human capital decreases. And then we have the role of space. So space itself, this neighbor effect, can explain about 4% of the overall convergence of Chinese provinces. Now, it's also very interesting to note here that physical capital becomes more important when we filter by the role of space, and human capital, on the other hand, actually becomes less important, meaning that the overall contribution to the convergence of regions diminishes from 16% to 13%. Now, these are the main results so far. We may think of including maybe panel data regressions and seeing how these coefficients change, but this is the relative importance. And this shows that, as usual, which is the case with spatial econometric studies, space matters. So it's not 0%, this contribution of the overall convergence that is space responsible for, is 4%. Overall, that's the main, let's say, the main outline of the paper. We can conclude by saying that the convergence of total factor productivity, aggregate efficiency, or productivity, whichever name you choose for it, explains most of the convergence of regional income for Chinese provinces in this period, 1998 to 2010. Now, the convergence of capital input accounts for about 30%, but moreover, space matters, and spatial effects are helping to reduce the regional income disparities in the case of Chinese provinces. Now, this is not always the case. Sometimes space does not help provinces in a country or subnational regions in a country to reach similar development or outcome or income or whichever variable you name or you study. So these disparities are explained by space, or let's say the reduction of these disparities. The disparity is explained by space, or the role of spatial effects. Now, what are the implications? First of all, that to spatially filter regional income and other variables is important because we want to avoid misleading interpretations. For example, when we run regressions, as I said, and we do not account for the role of space, then we have a problem with the error term. And that's quite common in the literature. Now, as I said, geography matters. So this is just, let's say, a simple paper. But beyond this paper, we know how important it is to break spatial barriers and continue to enhance the inter-regional connectivity. This could be, for example, in terms of infrastructure, as the Chinese government is doing, for example, in terms of high-speed trains, and cooperation of regions is highly important in terms of facing regions that are in the same geographical area of a country face similar problems, being rising temperatures to similar levels, pollution levels, disasters, connectivity issues, as I said, in terms of roads, airports, or even high-speed trains or trains. In general, connectivity is very important. And I would like to mention some next steps of this project. Well, we want to review more papers that analyze regional convergence in China. Unfortunately, we just focus on papers that have been published in English, because none of us, well, although Linda, my co-author, speaks pretty good Chinese, we are not checking the literature that comes from China that does not come in English. So unfortunately, that's one of the limitations. But we will continue to check the literature, and if you have any recommendations, any suggestions about literature, please let me know. Now, perhaps the second step should not be taken into account any longer, because we're taking an alpha of 0.3, and we've been checking some papers that use these or that find that this alpha in the case of China is exactly or about 0.3. So we are quite confident on that coefficient. Now we want to document and improve the Getis filter function, because although it's a relatively old method, there is no canned function to do that in R right now. So we have to write that function from scratch, and we would like to share it with the world. So we would like to be publishing this function with one of the packages for spatial data science in R. So that's the plan of this project. That's one of the goals of this project, to share that function. And also we would like to compare the results of this project with the results of previous papers, although it's hard to find papers that account for the role of space in the same way we do with my co-authors. And as you know, my name is Felipe Santos. You can check my personal website there. I am affiliated with the Chair of International Economics at TU Dresden here. You can see on the right, that's the website. And on the left, you can see the Quarks Lab. And Alvaro, if I'm correct, is also a member of the Quarks Lab. So we are together in this lab, and we're also writing some papers together. So that's all. Thank you so much. You can find all the references in the working papers. And also I send the link through the chat, so you can see a live website with these slides if you would like to check later, or if you have any questions, just let me know. Thank you so much for listening to this presentation.